it's still a very, very small signal. So how can you possibly see something like that? Is there any hope? And we believe yes, and here is another development that is driven by the Higgs search and other searches for very small signals. At the Tevatron, what you do is you use all the information that you have. You don't just look at that mass spectrum, but you look at, for example, so this is the mass spectrum. Here is the angular separation of the two jets. Here is the PT of one of the two jets. Here's the PT of the other jets, and then you have a few more quantities, and you put them all together, and you use something that's called a multivariate analysis. So, for example, a neural network. A neural network is just a nonlinear mathematical representation of a function that convolutes all these inputs, and you train it such that it spits out a number that's small, near 0, if the event is like the background, and it spits out a number that's near 1 if the event is like a Higgs signal is. And then you get a distribution where the signal has a rather different shape from the background distribution. And that gives you the maximum discrimination power between signal and background. And these methods have been developed over the last few years at the Tevatron. And I like this plot because it shows you the results, the limits set on the Higgs cross-section are these colored points. And they get, the cross-section limits get smaller and smaller as the amount of data that you have increases. And if it simply was the number of events that you get more, then it would go as 1 over the square root of the luminosity, or of the amount of data that you have. And those are these curves. So if we did this analysis and we just continued it, and all we gained was the amount of data, then it would follow this curve. But the latest limit is down here. So by improving the analysis techniques, huge improvements were made in the sensitivity of these kind of signals. Okay, still no Higgs signal has been observed, and you might ask, well, maybe this is all just pie in the sky, and you can't really see a signal this way. Well, here's a counterexample. The production of a single top quark, which is also a process where you have a signal to background of about 1 to 200 or something like that, was recently established at a statistically significant level by just using that kind of analysis technique. So here is a multivariate discriminant. Background-like events are near 0. Signal-like events are near 1. And if you zoom in on the high tail here, you see that you need this light blue component there, which is the signal part. I'm showing this because part of this work was done as a thesis by a Brown student, Monica Pangilinan. And here over here you see that the final state of single top production is a W that may decay to a charged lepton plus a neutrino, plus 2 Bs, one from the top decay and the other one from the top production here. So exactly the same final state as the Higgs boson channel that I just showed you. And here you can compare the cross sections of these processes. So this is the cross section versus Higgs mass. Single top production is here at 2 picobarn. The Higgs is about, depending on where the mass is, a small factor to an order of magnitude smaller than that. So we have to push about an order of magnitude beyond this, and we might be able to see a signal for the Higgs, or exclude it if we don't see a signal for the Higgs. So I think we are on the way to getting there. So what is the projection for what the Tevatron can do? And here now we're looking at something that's called a likelihood ratio. So this is like a discriminating variable for signal and background, and if there is no signal in the data, you expect that the value that you measure for this discriminating variable lies along that dashed curve. And the green and the yellow bands indicate what fluctuations you might see from what random fluctuations you might see from experiment to experiment. So 68% of the time you should be within the green band, and then I think 90% of the time you should be within the yellow band. Now, what you actually see when you analyze the data for the presence of different Higgs masses is this black line here. And the red line is the line that you would see if there were a standard model Higgs boson at this mass. And you see, for example, if you go to 160 GeV, we should be measuring a value of -6 here, and we're measuring a value of 4, which is exactly what you see if there's no Higgs boson. Whereas if you go to the low masses, then actually what we're seeing is very close to what you would see if there were a standard model Higgs boson. On the other hand, it's also very close to what you might see if there is none, so we just don't have the discrimination power yet. So what can we say? At this point, where we have the biggest difference between signal and no signal, we can actually start to exclude some mass range of a few GeV around 160 GeV. At the low mass, we're still a factor of about 2 above standard model cross-section with what we can exclude. So this here shows you the ratio of the 95% confidence level limit on the cross-section to the standard model cross-section. So when the black curve, drops below 1, then we've excluded Higgs boson production at the standard model cross-section. And with more data, of course, this will improve. Here are some plots that try to quantify that. This is the probability of excluding a Higgs boson versus its mass with 5 inverse femtobarn or 10 inverse femtobarn data. So with 10 inverse femtobarn data, we have a 50% chance or better to exclude Higgs boson over the entire mass range here. This is for the low mass region. And then in the high mass region, if you look for the WW decay, you can exclude something near 100